Good morning. So today's topic is Maxwell, Boltzmann, and Bose-Einstein statistics. During the previous lectures, we discussed Maxwell-Boltzmann statistics for disks and the spheres. For the two-dimensional systems, we discussed about this disk, and for three-dimensional materials, we discussed about the spheres. In this lecture, we will discuss general details of Maxwell-Boltzmann statistics. We will introduce bosons and fermions, and also we will introduce Bose-Einstein statistics. And also we will mainly focus on chemical ensemble, where the number of particles and the volume and the temperature are constants. So Maxwell-Boltzmann statistics, also called the classical statistics. In this, we consider multiple particles, and these multiple particles can occupy any energy state, and particles are distinguishable but identical. So distinguishable but identical. What does it mean? So if we have two particles or three particles, let's say, we consider that these are identical. That means all these particles have the same features, and maybe the radius of all these are equal and everything is equal. However, the Cartesian coordinates or any coordinate systems, they are at different locations. So that's why we say that these particles are distinguishable. So this one is at R1, this one is at R2, and this one is at R3. They have negligible interaction energies based on Maxwell-Boltzmann statistics, and also we can show, we can consider the ideal gas as an example for MB statistics, because the interaction between the ideal gas molecules are negligible, and we consider they are just moving randomly and collide with each other. So any permutation of two particles in different energy states must be considered as a distinct state of whole gas, even though the numbers N1, N2, N3 are constant. So here N1 means the number of particles at the energy 1, energy state with the energy epsilon 1, and 2 is the number of particles at the energy state with energy of epsilon 2. Likewise, we have a set of simple n values which are related to the each energy state. So the partition function in canonical ensemble can be written in this form, where we here where we have factorial capital N. Here N means the number of particles. This is the number of particles, and we have factorial n, and we divide this by factorial n1, factorial n2, and so on. Because any permutation of two particles in different energy states must be considered as a distinct state. And then we have this exponential function. So this factor times exponential of minus beta times n1 times epsilon1 plus n1, n2 times epsilon2 plus so on. So this is the partition function in canonical ensemble for Maxwell-Boltzmann statistics. So if you have some values, and if you calculate the sum of it, and then to compute the nth power of that sum, we can expand that summation using this expression. So here we have sum of factorial n over factorial n1, n2, and up to nk, because we have k number of x values, and there are n1 number of x1 values, and so x1 to the power n1, x2, there are n2 number of x2 values, so x2 to the power n2. Likewise, this product is going up to sk to the power nk. So so we can expand this power of sum of multiple terms using this expression, and therefore since we have this expression for partial function, and also this takes this form, we can write the partial function based on this expression. So we can write this summation of exponential of minus beta epsilon I to the power n as the partial function. Because here for each x value represents exponential minus beta epsilon I. Epsilon I. So based on this partial functions expression, therefore we can write this in this way as a sum of these exponential values, and then we can calculate the power of n to the this summation to the power n. So this summation within these brackets is denoted by simple n, and this is capital N. So capital, sorry, simple Z. Here we have capital Z. So capital Z is equal to simple Z to the power n. This capital N is the number of particles. So this simple Z, it is the particle function for single particle. It's the particle function for a single particle. So we derive this expression for the particle function of the system based on the particle function of a single particle. And then if we want to calculate the mean occupation number, which is denoted by ns bar, here S is the energy state, S denotes the S energy state. This is the mean occupation number at the energy state with the energy epsilon s. So this can be computed using this expression over here. So ns bar is equal to minus 1 over beta dabba ln of z over dabba epsilon s. So we differentiate log of z with respect to the energy of the relevant energy state. So we know that capital Z is given by this summation to the power n. So if you differentiate this, you will get n times exponential of minus beta epsilon s over sum of exponential of minus beta epsilon type. So this is what we get. So we know these terms because here we have exponential of minus beta epsilon s, but over here this is the partial function of a single particle. So based on this, we can write ns bar is equal to psn. Ps is the probability of occupation of the energy state S by a single particle. So the probability of occupation of energy state S by a single particle. So it gives us the possibility of occupying some energy state by a single particle. So it is equal to Ps. It is denoted by Ps, and it is equal to exponential of minus beta epsilon s over simple Z. Okay, now we want to calculate the internal energy. So internal energy is denoted by U. That is the average energy of the system. The average energy is denoted by these brackets, within these brackets, E. So it is equal to the number of particles times sum of Pi times epsilon time. So here Pi is the probability of occupying some energy state by a single particle. And then we can rewrite Pi as exponential of minus beta epsilon I over Z. And then you can easily show that if we differentiate, Z, so we found that Z is equal to a sum of exponential of minus beta epsilon I. So exponential of minus beta epsilon I, and then if we differentiate this, differentiate this with respect to beta, what happens is if we differentiate this, we get and then exponential term does not change. Okay. So so you can see that we can replace this sum over here, this part, with double Z over double beta, because Z is just a constant, so we can take this over here. So we have also minus sign. So basically we can write this expression in terms of WZ over double beta, and this 1 over Z double Z over double beta, this is equal to double logarithmic Z over double beta. So so we get this expression over here. So so let's look at some example. We try to explain some paramagnetic system based on the MB statistics. So in this one, we consider that electrons as classical particles, so they obey the MB statistics. So each electron is considered as spin, because electrons can rotate around its own axis, right? It can rotate in this way or in the other way. So based on sorry, the directions should be changed, I think. Anyway, so they can rotate around their own axes. So so each energy system has energy based on the uh, direction of the rotation. So if it rotates with the spin up, uh, so here I have to correct something. Direction should be changed. Uh, Here this is the direction. Anyway, so basically, spin up particles, because its axis is in the upside, so the spin up particles have a positive spin value or magnetic moment. Uh, Spin down particles have negative magnetic moment. So based on the magnetic moment and also the external magnetic field, it can have different energies. So for this system, we have two energy states. Energy state of the spin-up particles have a silent one, which is equal to minus mb, and spin-down particles, the energy state of the spin-down particle has the energy of mb. Because energy is given by minus mb. Let's say this is let's say okay. Let's say this is mu. So here mu is positive mu, and here here we have negative minus m as the mu. So if you substitute this mu with positive m, we get minus mb. If you substitute this one over here, we get positive mb, because we have minus m here. So epsilon 1 is equal to minus mb, and epsilon 2 is equal to m, capital M, positive mb. So we consider that these particles are identical but distinguishable. So here you can see some program to calculate the partition function value and the mean numbers for each energy state and mean energy values for each energy state. So in this example, we consider 100 particles, which can be in either mb or minus mb energy states. So to make it more convenient, we consider that m is equal to 1 and b is equal to 1 in their appropriate units. So in the program, here we mention the energy values. So minus 1 and plus 1, those are the energy values, because we consider that m is equal to b is equal to 1. So minus 1 and plus 1 are the energy values. And we have some dictionary for mean n values of each energy state, and we consider beta as 1 to make it more easier, and we can calculate the total energy by calculating the sum of these energies, and total number of particles is 100. So in total denotes the number of particles in this program. So we know that first we need to calculate the partial function. To calculate the partial function, first what we have to do is we have to calculate the partial function for a single particle. That means simple Z. So that is what we are doing here. We are calculating the partial function for single particle. However, for next we are calculating the partial function of the system. So that is the partial function of the a single particle to the power number of particles. So that is what we are doing over here. And then here I'm calculating the mean in value for each energy state based on this expression over here. So we can compute it. And also we need to calculate the mean energy value. So to calculate that, I'm using this expression over here. So okay. So next we try to derive some expressions for these particles in this example. So Z is equal to that, or the partial function of a single particle is equal to exponential of minus beta epsilon 1 plus exponential of beta epsilon 2. So epsilon 1 is equal to minus mb, epsilon 2 is equal to positive mb. Therefore, we can calculate this, and this is equal to 2 times hyperbolic cosine of beta times m times b. Next, we are trying to derive some expression for mean number of particles for given state, energy state. So it is ns pi is equal to ps times n. Here ps is the probability of occupying some energy state by a particle, and then we calculate P1 and P2 for each energy state. So P1 is equal to exponential of minus beta epsilon 1 over simple Z, and P2 is equal to exponential of minus beta epsilon 2 over simple Z. And then we have the expression for simple Z, that is the partial function for single particle. So we have these exponential functions, and in the numerator, we substitute these energy values for the relevant energy states. So energy values. So by simplifying this, we are getting these expressions for P1 and P2, and then if we multiply them by the number of total number of particles, we are getting mean number of particles at each energy state. Those are N1 bar and N2 bar. And And next thing we need to calculate is the internal energy. So to calculate the internal energy, I'm going to use this expression which we were deriving. So so we know that simple z is equal to hyperbolic cosine over hyperbolic cosines of beta times m times p. So I can plug it here, and I'm getting uh, this as the internal energy. So internal energy is equal to minus n times m times p hyperbolic tan of m b beta. So today I'm introducing bosons and fermions in this course. So these are two type of particles we will meet. We meet in quantum mechanics. Uh, so in the quantum mechanics, the wave function of a particle uh, is given by uh, as a function of the position and the spin. So x has the x is the x denotes the coordinate and s denotes the spin. Let's assume there are two particles. Particle 1 is at x1 and it has spin s1, and particle 2 is at x2 with spin s2. So the wave function psi is a function of x1 s1 and x2 s2. Now, if we flip the particle positions, x2 goes to x1, and x2 goes here, and this one goes here, and that one goes there. So therefore, we can have two different wave functions when we are switching the positions of the particle. And then, if the particles are identical, we can write their magnitudes are equal. So if we calculate the magnitude squared, it is equal to magnitude squared of psi of x1 s1 x2 s2. It is equal to the magnitude squared of x2 s2 x1 s1. So actually, square of the magnitude must be equal if the particles are identical. Okay, now we have this expression, and since wave functions are complex numbers, they can only differ by a phase if the modulus are equal. So we can write uh, the magnitudes of a psi of x1 s1 x2 s2 as a tau times psi of magnitude of psi of x2 s2 x1 s1. So tau is the phase. Tau is the phase, and that is also equal to exponential of I theta. Therefore, the magnitude of the phase is equal to 1. And then, if we, since we have this expression, I label this as 2 and this one as 1. And what we can do is now we can calculate the square of these two. And then we know that this one is equal to this. So we have square of magnitude of psi of x1, x1, x2, s2 is equal to tau squared square of magnitude of psi of x1, s1, x2, s2. So you can see this one and that one, these are equal. Therefore, tau squared is equal to 1, and tau can be plus or minus 1 because square of tau is equal to 1. So if tau can, or the space can have two values, those are plus 1 and minus 1. If tau is equal to 1, we call it a boson. If tau is equal to minus 1, we call it a fermion. Tau is equal to 1 means the wave functions are symmetric. That means even if we exchange the positions, the wave function is symmetric because this is equal to 1. If it is minus 1, when we interchange the positions of the spins, we get the negative magnitude. So it is antisymmetric. The fermions have the antisymmetric property for the wave functions, and the wave functions are symmetric for bosons. Okay, now for the particles with the particles with integer spins, that means S is equal to 0, 1, 2, 3 are bosons. The particles with half integer spins, like 1 half, 3 halves, 5 halves, are fermions. So this correspondence is called the spin statistic theorem. And bosons obey Bose-Einstein statistics, and fermions obey Fermi-Dirac statistics. So today we are explaining or discussing the details of the Bose-Einstein statistics, but next time we will go through the Fermi-Dirac statistics. So based on the Bose-Einstein statistics, multiple particles can occupy any energy state, and particles are distinguishable and identical. They are distinguishable and identical. That means we cannot locate the position of the particle. So it is so difficult to understand the position of the particle. So these are indistinguishable and also identical. So some examples are photons and phonons. So the particle function in canonical ensemble, the is given by this expression over here. Here, capital Z is equal to sum of exponential of minus beta times n1 is silent 1 plus n2 is silent 2 and so on. So Ni is the number of particles in the ith energy state with energy epsilon time. So here we calculate the summation over all the number of particles at the at each energy state. So here N1, N2, these numbers are independent from each other. Okay, these are independent from each other. Therefore, we can write this summation in this form. So these are products of these summations. Therefore, the total partition function can be written in this way. So this is the summation. These summations are given by this sum. And since this is a product, we have this symbol over here. So here the symbols denotes the product, and it varies from S is equal to 1 to number of energy states. So if we have some numbers x1, x2, x3, we can write this as xi I is equal to 1, 2, 3. So this is the product, okay? This is product. X1 times, x2 times, x3. So this product can be written in this way. So that's what we are doing here. So we are calculating the product for all these summations. So we have to do this for each energy state. That's why it goes from 1 to the number of energy states. Okay, so average number of particles in its energy state is given by n bar as ns bar, and so ns bar is given by sum of ns times exponential of minus beta ns times s over sum of exponential of minus beta ns epsilon s. And we can also write this as ns bar is equal to minus 1 over beta times dabba ln of z over dabba epsilon test. Okay, now we have another example, and this is about the Bose-Einstein statistics. So we have some bosons, and we consider beta is equal to 1, and we are considering 100,000 particles. 100,000 particles. And there are 5 energy states indexed from 1 to 5. Each energy states have these energies. 1, 2, up to epsilon 5. We have these energies for each energy state. So I wrote this program to calculate the partition function of the system, and also the mean occupation number for each energy state. So these are the energy values in the table, and we can calculate the total energy by calculating the sum of energy values. I don't think it is needed for this, even though I calculated this, so you don't need to worry about it. And then then yeah, this is not required. And what we want is we want the total number of particles, that is 100,000, and then we are calculating the partial function of the system based on the partial function for each energy state uh, in this way. And based on that, we can calculate the mean occupation number for each energy state based on this expression over here. Okay, now we have this partial function for based on Bose-Einstein statistics, and since these n values, simple n values, are independent, I was telling you that we can write this summation as a product of summations, total summation as a product of summations over n1 to nk. K is the number of energy states. And then now we are considering a infinite number of particles. That means capital N goes to infinity. So this summation is from n1 is equal to 0 to infinity. So this kind of summation can be written in this form, or can be written as 1 over 1 minus exponential of minus beta times epsilon time. So we can write each sum in this way using in this form, and then this partial function is equal to product of 1 over 1 minus epsilon of minus beta times epsilon 1 epsilon time. So if you calculate the natural log of capital Z, we can calculate ln of this product. However, we know that logarithmic product rules of logarithmic. So it is A times B, ln of A times B is equal to ln of A plus ln of B. So that is what we are doing here. This is the product of all these terms, and now I can write this as sum of ln of this 1 over 1 minus epsilon of exponential of minus beta times epsilon time, and then I can rewrite this in this way. And therefore, we have some expression for natural log of listen. Here k is the number of energy states. So so we can calculate the average number of particles in S energy state using minus 1 over beta times dabba ln of z over dabba epsilon s. So we can differentiate this with respect to epsilon s, and we get this ratio, and based on that I can simplify it and find that ns bar is equal to 1 over exponential of beta epsilon s minus 1. So so this is valid for canonical ensemble, and this is called Planck's distribution. So you learn about the Planck's distribution for modern physics, if you learned that before. So, and you can see that based on these Bose-Einstein, the basics of the Bose-Einstein statistics, you can derive Planck's distribution. And in chemical ensemble, the total number of particles n is a constant, and photons are bosons. However, photons, number of photons is not conserved, okay, because it can absorb and emitted. So number of photons is not conserved. Therefore, instead of considering the number of photons, we can consider the chemical potential. The chemical potential is the energy required to remove some particles from some material. So we can consider that instead of the number of particles, number of photons. So we use a grand canonical ensemble um, instead of chemical ensemble. In the grand chemical ensemble, the chemical potential, the volume, and the temperature are constants. So what we have to do is we have to reduce the chemical potential from each energy value. And I think it should be over here. And so we can show that uh, 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 mean occupation number of the S energy state is given by 1 over exponential of beta of epsilon s minus mu minus 1. And this is for a discrete system where the energy values are discrete energy values. And if it is like a continuous energy spectrum, then we can consider this mean occupation number as some function of the energy. So n of epsilon is equal to 1 over exponential of beta times epsilon minus mu minus 1. Okay, so here I am explaining how to derive uh, this uh, the radiated power by a black body based on the Bose-Einstein statistics. So you can go through this. The important thing here is we can understand how to derive this kind of basic things in with basic things we learn for modern physics based on the basics of the Bose-Einstein statistics. Okay, that's all for today's lecture. Thank you.